welcome to the SZ4Grads Spring Webinar Series. So my name is Aqeel from the University of Wisconsin-Madison. So I'm today's webinar's host. So this webinar is organized by SZ4D and SZ4Grads. So I would like to first introduce them. So SZ4D stands for Subduction Zones in 4 Dimensions, and is a community-driven initiative for a long-term interdisciplinary research program to understand the limits and possibilities of predicting geohazards in subduction zones. SZ4Grads stands for Subduction Zones for Graduate Students and Recent Grads, and is a collaborative, interdisciplinary, and intercultural network for early career researchers studying subduction zone processes. Before I introduce today's speaker, there are several things I want to mention. So first, so we hope you can fill in a survey during or after the talk to provide us some feedback about this webinar. So I'm now copy and paste the link for the survey in the chat. Yeah, so hope everyone can see the link. So I also want to remind that the live translated captions are available, so you can turn on this option if you need. And also the recording of this webinar will be posted on SZ4D YouTube channel. So all right, let's move on to today's talk. It's my honor to introduce today's speaker, Aqeel Abbas. Aqeel is currently a PhD student in cosmology at the Chinese University of Hong Kong. He earned his master's degree from Zhejiang University in 2020. So his current research is mainly focused on understanding induced earthquakes due to hydraulic fracking in the Wenyuan shale gas field in Sichuan, China. He has also been working on addressing some issues with temporal seismic data, particularly the clock drift issue in OBS data, which he is going to talk about today. So all right, let's welcome Aqeel for today's talk. So his talk, the title of his talk is Evaluating and Correcting Short-Term Clock Drift in Data from Temporary Seismic Deployments. So Aqeel, please take it away.
Thank you so much, Go, for nice introductions. So hello, everyone. I'm Aqeel Abbas, a final year PhD student at the Chinese University of Hong Kong. So today I will share a part of my PhD work about the clock inspection in temporary seismic networks. So I will try to follow up this outline where mainly we discuss the existing problem in the OBS dataset, but at the end I will just show a brief overview of clock drifts in the land datasets because I'm currently working on the induced earthquakes. So most of the contents come from this paper that we have published in last year. So if you want more details, you can just follow up these papers. So OBS has been widely used in water velocity structure using body and surface waves. And the data is very precious due to high cost of deployment and unpredictable recovery of equipment and data, because most of the time we lost our instrument and it cost too much to have an experiment of OBS. So in this work, we utilize the OBS station across the Mariana subduction zones, which is located at the boundary of Philippine plates and the subducting Pacific plate. So Mariana plate is divided into 3 parts: north, central, and the southern Mariana parts. So to understand the subducting plate bound geometry, a near-field seismic network is necessary, but it is only available for central Mariana Trench. So in this park, we deployed our station along the southern Mariana Trench in 3 different time periods. So this southern part holds the oldest oceanic crust, and the Earth's deepest part is called Challenger Deep. So as the closest station, land station is the Guam, which is around 350 kilometers far away from the southern Mariana Trench. So we must need to fill this data gap to understand what's going on this deeper trench. So we conduct the OBS experiment near the Challenger Deep and obtain the first data set for 6 months from 2016 to June 2017, which is highlighted with the red colors. And in the next years, we deploy the second OBS stations, which also are the 6 in numbers from February 2017 to June 2017. So this cover mostly the region of incoming plane on the outer trench slope. So for the third deployment, 5 stations were deployed, which are highlighted with the yellow color for 1 year, primarily covering the southern West Mariana Ridge. So red station refer to the previous 2 field trips that I just shared in the last slides. So we have quite a huge data set and we'll spend a lot of money. So we want to utilize it as much as we can. So however, these stations often suffer clock errors, which are crucial for multiple geophysical applications such as earthquake relocation and seismic tomography. So for instance, an average clock drift is around ±2 seconds per year from 700 OBS deployment, which may exceeds up to tens of seconds. So it's quite common to observe such kind of clock drift. So it's due to the fact that the GPS doesn't work in the marine environment because the signal cannot propagate far in the water. So we have to inspect and correct the clock errors before further utilizing it. So these are the mostly patterns that we have observed during our work. So normally clock drifts refer to some linear and continuous changes which are easily estimated and correctly. For example, in most of times we have the abrupt or the linear trends, but sometimes there are non-linear drifts still exist which can last for the whole deployment period or for a short time windows, so which are very complicated to resolve. So there is one of the most direct and robust method for clock inspection is from the differential travel times between by using the earthquakes from the predicted, we can utilize the predicted and observe arrival times. So for example, it is assumed that the differential time on each station should be consistent with others if clock is operating normally as the source and the location path is consistent. There is no change along the path, so they are identical. So we believe they should have the similar observed and predicted arrival time. There should be not very rapid change. But we have found like some events, this H36 station observe up to 15-second drift on several events. So we find this station is very abnormal to detect some very sharp changes. For example, in the Goha et al., she observed the clock drift on the one station by using several events, and we just connect the time shift from one event to the last event. So in this case, we cannot observe it cannot represent the timing error over the entire deployment period due to the limited number of earthquakes that can be few of them. So to overcome this gap, we utilize the ambient noise cross correlation, which is very commonly utilized. So during this process, we use the daily noise data set from 2 different stations, and there is one main assumption that noise must be homogeneous. We just cross correlate it, and we get the ambient, we get the result cross correlation function, which have the casual and uncasual component. So if they are very symmetric, then it's mean there is no time error if the noise is homogeneous, and if symmetry is broken, then it's mean there is a time shift. I will show you the very practical example from one of our land data set. So the color image represents the cross correlation function for the whole deployment periods. So the black line is the stacked window. We normally stack the ambient noise cross correlation to improve the signal to noise ratio. So this station have been working perfectly well in the first half, but later there is a sudden jump and then it remains constant. So ambient noise is very good to find any sharp changes in the clock drift, but it fails to address some key problems such as the resolving the sub-daily time drift or clock drift errors within the selected stacking window. For example, if we stack for 2 days and the clock drift occur only within 1 day, so how we can solve these problems? So this problem we observe in one of our stations in 2020, Joe et al. Shows one station where we have the time errors up to 90 seconds in different time periods. So these short periods could not be detected with daily data using cross correlation function when we stack for a few days. And ultimately, we have to discard this part of data set, which we really don't want after spending a lot of money and when the stations are very limited. So how we can solve this problem with ambient noise cross correlation functions? So I have used the third field experiment to correct some stations. So I have used the both teleseismic event and the local events and calculate the differential time for 5 stations that we have used. So we find there is a two events. We have up to 20-second clock drifts for one station 36, which is highlighted with the red dots. And 9 events are observing the clock drifts for using local events. We have set the threshold up to 10 seconds because this is the subduction zone environment, so we cannot expect these are the time drift. It could be the heterogeneity due to the subduction. So we only prefer that are very significantly far from the centralized line. So we notice that the clock drift appear and disappear for 2 events recorded even on the same day. If we look at this only this zone, so we have the clock drift up to 20 seconds, and after a few days or even within 1 day, we find the station is working very normally for a very long time window. So we were very curious, like how it happened and how we can solve it. So here is one example. So we observe on one event one, which is occurred in Southern Mariana on 2018. We find the clock drift is up to 20 seconds. And on the same day, after 3 hours, there is another event in the Caroline Island. This station seems to be normal, so there is no clock shift. So it's something happened within. So clock drift being to be normal of within 3 hours. So if we clock drift will remain in the data if we use the daily waveform data set, we stack for a very long time. So it's very crucial to carefully select the data length and the stacking video to avoid sub-daily problems where we find the clock drift within 1 day. So for this problem, we come up with different solutions. So we compute the cross-correlation functions for different time windows up to from 24 hours to 3 hours in a daytime. And we stack for different time windows. So we have one standard, like we will compute this noise cross correlation function for different segments. Then we verify those clock shifts from our waveform inspection that we have done using the events. So this is the cross correlation function for 24 hours. And this is the zoom view of one of them. So we can see there are some peaks that are far away from the normal lines. So when you look at the 24 hours, there are some very clear trends. We can find some time drift in this event. But when we compare with our observed clock shift from the earthquake events, most of them are missing from 24 hours. Then we come up to the 12 hours. When we go to below to the 12 hours and stack for 5 segments, we find there is some improvement in the clock drifts. We can detect more clock drifts when we go to the 12 hours. So we try to go to the 6 hours. 6 hours is very consistent with the 12 hours, but it is successfully can detect the clock drift within first week, which was not appear in the both earlier segments. So we believe our results are going to be improved at this stage. We almost detect all of the clock drifts that we have observed in the previous slides. So humans are greedy. So we go to the 3 hours to check what happened. So when we done the clock drifts, so when we compute the cross correlation function for 3 hours, we find that the signal to noise ratio is going to be destroyed. And there is a kind of trend of clock drifts when we go to the 3 hour segments. And most of them are not existing in our observed clock drifts, but due to the poor signal to noise ratio, we can also not rely on 3 hour segment. So there is a kind of trade-off between detection efficiency and noise level for each segment length. So after analysis of all cross correlation pairs, I have to just mention. So among the 4 of them, only 6 hour segment was very clear and detect all of the able to detect most of the short period clock drifts that with distinct similarity to drift detections from our previous observed waveforms. So we go through with that one. And after analysis of all cross-correlation pairs, we observed that out of 5 stations, 3 stations suffered with clock drifts. Station H33 and K06 have very linear clock drift. If we just zoom out, station H30, station K06 have 0.25 seconds clock drifts, and stations H33 have 0.56 second clock drifts. That is very linear and very commonly observed in different OBS environment. But if we look at the station H36, so beside the linear clock drift, which is around 2 seconds, still higher than above 2, we observe the clock drifts up to 4 second to 33 second fluctuation throughout the time. So we have recalculated the clock drift. So this is the before correction. So we can see there is a linear drifts, and we can observe some peaks. So we have correct those clock drifts and make it very symmetric for both of them. The black line is just for reference if it's well aligned. So for linear clock drift, it was very easy to correct it because it's just like a very simple trend. But for this one, we tried to successfully correct all of the sharp drifts, and our results prove much better than previous ones. So we are able to recover this station, which was very important because we have only 5 stations, so one was going to be discarded. So we verify all of these clock drifts before correction and after the correction with ambient noise and still with our reference clock drifts that we have observed from earthquakes. So there are some takeaway message like stacking window must be decided based on minimum interval of 2 observed clock drifts. The first reference must be from the earthquakes waveforms to observe how much stacking window we should have. And the second, the cross correlations using small segment of daily waveform can significantly improve the detection capability. And in most of the studies, the daily cross correlation has been used, but it has no scientific justification except for ease of data access. So we mentioned we have to utilize the segments on some kind of reference. So those reference can be set by waveform observations. So we have verified the data before and after the correction to make sure that the clocks are reliable, in reliable condition to further utilize it. So this was very simple techniques to improve our detection capability to solve current problem in the OBS dataset. But I will just go through from the land dataset to just give you an overview of what kind of problem we faced during the land dataset, because currently I'm working on the induced earthquakes, so I can also show some slides. So I'm working on the Wuyan shale gas field, which is one of the China national demonstration areas for shale gas development in the Sichuan basins. So we have deployed one dance array along the Mulian fault, which has 76 stations with interstation distance of 50 meters. And we also deploy some mini arrays along one of ongoing operation of hydraulic fracking to monitor what's going on. How can we understand the induced seismicity? So this dense array was preferred to understand the fault geometry along most of the hydraulic fracking wells. So these white pentagon refer to the hydraulic fracking wells. So you can just imagine the intensity of fracking in these regions. The same thing, we have used the teleseismic earthquakes to understand the clock drifts. So in most of cases, there was very identical trends that we have find in the OBS data. So there are some linear trends, but at the most of time, at the end of our deployment, because these density were deployed for 2 months, so we find most of the clock drifts appear in the last month. So it was just due to the weather problems, because our station was just buried a bit down of the one feet or maybe some feet down to the earth to avoid any potential harm from the people or from the animals. So one of the main problem that we faced, like our density was deployed close to the city. So you can find the roads and some reservoirs. So for the noise cross correlation function, we have one condition: the noise must be homogeneous. But in the city, the noise is not homogeneous at all. So we choose the 9 land station, which we verified these are correct based on the waveforms and on different distance, like this density is on the 5 kilometers. So we choose 9 station at different distance up to 3 kilometers. So when we check the wave ambient noise cross correlation function for different distance, so it is going to be distorted with when we are going to increase the distance. For example, up to 600 or 100, 1000 meters, the ambient noise is very stable. There is nothing changed. But when we are going to far away from the two reference stations, the ambient noise is going to be distorted. It seems like there are clock drifts, but these are not clock drift. It's just like the noise is not homogeneous at all. So we assume that we must need to do the cross correlation within 1 kilometer because we have multiple stations, so we can subgroup our density into different groups and further inspect the clock. So the noise is very stable for the 1 kilometer, and where we have very unstable noise for later over 1 kilometers. So we find one solutions like, sorry if it's the okay. So we divide our density into different groups. Every group have 5 stations with different colors you can have seen. So first we calculate the ambient noise cross correlation within 5 stations. So the 5 station is even less than 1 kilometer. It's about 500 meters. Then we done first intergroup cross correlations for every stage for every group. Then we choose one station from the previous group and cross correlation with the next group. It's like intragroup ambient noise cross correlation. So the purpose was that we want to make sure that the density, all of the station on the density are well aligned with each other on the same time. So when we utilize this trick, it worked very well. So we try to avoid the non-homogeneity in the noise. So we try to keep homogeneous when our stations are deployed within city. So we find like out of 79 stations, 13 stations with clock problems, and we have successfully correct all of them. So we in the land data set, we don't need to stack it because the signal to noise ratio is quite nice compared to the OBS data set. So we don't stack those data sets, and we just cross correlate with the daily data set. So we can see there is like a very randomly trend of our clock drifts, and on this data, there was one station was not working at all, so it was not clock drift. So we try to solve all of the clock drifts and solve it very clearly. So we find like on some station have clock drifts up to 3 seconds. This is the maximum we have observed in our density. But we find different patterns in the clock drift. For example, there are some clock drifts in the last month, which is very linear. But in the next group of stations, there is abrupt change, but later it goes to be the linear. So the important message from land data set is that we must need to make sure if we want to do the noise cross correlations, our noise must be homogeneous. Otherwise, we may ignore or we may correct some already corrected data set. So here from the land data set, the takeaway message is just like we must need to carefully select the interstation distance, which can significantly improve the cross correlation results and reduce the intense localized noise. So that's all from my side today. It was very short presentation. So if you have any question, just let me know. So this data has been utilized in several papers. So this is our group website from Professor Yang Hong Feng. So you can find all of the research from this data set in this QR code. Thank you so much.
So, all right. Thank you so much, Aqeel, for the excellent talk. So next, we would like to open for any questions the audience may have for you. So please type your questions in the chat. So okay, so I can actually I have questions for
Yeah, sure.
you. I'm curious. So if you done any test with synthetic or real data, uh, for if you use the how the clock drift error affect the result of like tomography, like the body wave tomography or ambient noise tomography results, with um and without the correction of the um time errors
Yeah,
in
it
OBS
feels
data
like
and also in both OBS data and also in the onshore data.
yeah, it depends on the like available stations. Like in this case, we have only 5 stations. So if one station has suffered too much with the clock drifts, then we cannot get the clock, we cannot get the earthquake location very precisely if the clock drift is up to 20 seconds. So we must have to discard these stations if the clock drift is too high. Then we left with only 4 stations. So these 4 stations may not be enough for to resolve the earthquake locations in different scenarios. For it is very important for OBS dataset to correct the clock drifts if we have very limited stations. If we have very few stations, we cannot do anything if we have very limited station, then because the coverage will be very less in very narrow zones. So it's for the land data set, if we have enough stations, we don't need to care about it. We can simply discard it.
So have you compared results like doing tomography with
No, we haven't done with we have done the comparison because we when we done the earthquake relocation in different setups, it's very important. We can get very significantly different results because the arrival time is different. So all of the tomography, especially arrival time tomography, is based on the our peaks. So if the peaks are wrong, then it must be influence our final models.
yeah, I agree. So I think it's nice to see such a comparison. All right, so let's see if our audience has any question. I have another question. Could you go back to the slides showing how you detect the clock error using ambient noise cross correlation?
So it's like we use the ambient noise from 2 stations. Like we use the band pass up to 1.5 to 2 seconds. So we must need to set the band pass filter to avoid any kind of events in those data sets. So it should be the pure noise. Like we have excluded the any signal from earthquake. So it will be like a very homogeneously noise. Then we just simply cross correlate. So if the noise is homogeneous, then from station B to A or A to B should be very similar. There should be not influence from anything. So we have to set the band pass filter to make sure there is no influence from the outer source. So this is pure noise signals. So we do for every day. We do the ambient noise cross correlation for every day. And then we just simply, in the land dataset, we don't need to stack it, but in the OBS dataset, we must need to stack it because the noise is too poor. So we have to stack it to improve the signal to noise ratio. So this is like a stacking window. So we calculate the ambient noise for every day, and then we just plot with respect to the time and the lag time. So it makes us very simple. I have shared my code on GitHub. If you are interested, I will just send to you, or even it's available on my web page. Yeah, here is my web. So I have shared all the scripts how we done the clock corrections in both land and OBS dataset. And this paper is like about the clock drifts in both land and OBS dataset, so it might be helpful.
Okay, thank you. Another question is about the body wave part. So you So there are only two in one size. There are only two tiny earthquakes having this clock issue, or maybe two earthquake or two stations. But there are 9 local events having this issues. Is this difference because of the number of events being used, or?
Yeah, it's the number of earthquakes, because in the teleseismic events we find there is only, I think it's around 12 or 15 events that we have find the teleseismic events with good signal to noise ratio. And for the local earthquakes, we find too many because of the subduction zones. So we find too many local earthquakes in different intervals of time, but still we find there is a huge gap during some times. So that's why we don't find too many sharp drifts in the teleseismic event. It's just because of less availability of good teleseismic events during that time. But as we are working on the subduction zones, so we can find too many local earthquakes to just observe if there is any clock drifts. But we have to make sure, like in subduction zones, the clock drifts, time delay can be possible from the heterogeneities from the subduction zones. So that's why we set a threshold like up to 10 seconds, so which is the maximum time shift we can see. Like it's impossible to have 10-second drift from even in the subduction zone. So we find still too many from same station, we find too many clock drifts. So station is consistent, just the time drift is very fluctuated. So this kind of work is like a quick check to check your data set even before going to the ambient noise or something. So we must need to check events waveform for a few of events, then we can see if data is in good conditions or not.
Thank you. Let's see if there are any other questions. Okay, so if there's no more questions, let's thank Aqeel again for his excellent talk today. And don't forget to fill in the survey to provide us some feedback about this webinar. So thanks everyone again for your presence today, and see you next week. Goodbye, everyone. See you next week.
Thanks so much. See you next week.
Bye. Take care.